Okay, ladies and gentlemen, I know I am the one who's standing between you and the gala dinner, so thanks for staying. I will talk a little bit about the concept of a wearable sensor for measuring sounds from the torso, from the thorax. And yeah, after the previous talks, I would like to ask you for excuse that we're still at a very early stage of the project. So I will present the hardware setup and first measurement results on that. Then let's step right into the introduction. What are the sounds that we are interested in and what are the information that they carry? So first of all, you will think about heart sounds and lung sounds as the typical types of sounds that you would get from the thorax. So heart sounds is some kind of mechanical counterpart to the ECG. So you get the mechanical cardiac activity, so the actual contraction, compared to just the stimulation part that is given by the ECG. Then you get, of course, the heart frequency from the different heart sounds, and in the case of pathological signals, information about valve insufficiencies. Similar in the case of lung sounds, in the normal subject, you can derive breathing frequency and amplitude. So in the particular case, also shortness of breath, which is a highly relevant information when you want to monitor congestive heart failure, for example. Then also, breaks in the breathing, so particularly sleep apnea, and also pathological sounds like wheeze, rhonchi, crackles in the case of respiratory diseases like COPD, bronchitis, and so on. But also apart from disease management, you can have a look on cases of elderly care. So particularly in the elder persons, you can have aspiration of ingesta, so a measurement from the windpipe. And if you go more to the bottom of the body, so you can also have the peristaltic sounds, so information about obstipation, and in the critical state about ELE. So normally you would say, well, I'm just interested in heart sounds, but particularly when you aim at elder persons and patients with chronic diseases, there's typically a whole bunch of diseases and problems that these people suffer from. So you should normally, or you are interested in monitoring several of these heart sounds. So our aim is now to get information from different sound sources. So our long-term goals, or the basic goals of the whole project are, first of all, long-time monitoring of the thoracic sounds. So for example, in the elderly care or for chronic diseases. As I said, we want to evaluate different sound sources, and this all should be done by automatic signal analysis, and the information then should be provided to the treating physician or the or the care personnel. So our approach is to use, first of all, several acoustic sensors, not just one, as it typically done, in order to focus on these different sound sources, either by using separate sensors for each source, or, which is the actual goal, to realize some directional filtering and focusing with several microphones on a specific sound source. We use small size electrode microphones in contrast to the typical cut-off stethoscope heads that have been previously published. And in the long run, we would like to integrate this sensor system in an already existing sensor platform that we developed for dementia care. So here short a photo that incorporates fall detection and localization. And we're currently extending this plaster, this healthcare plaster, by additional sensors. So in the far future, we would also like to fuse the acoustic data with other sensor data like ECG activity and so on. So what have we done? So here is the first prototype that we are proposing here. So you have the main PCB with energy supply, analog signal conditioning, and the Bluetooth connection. The microprocessor is in this first stage on an evaluation board by Texas Instruments, and we currently have 4 microphones to capture the sensor data from the thorax, plus an additional one that you can see here above, which aims for ambient noise. And then, so after capturing the sounds, we do an amplification, then bandpass filtering, conversion to digital domain, and after that, get the Bluetooth connection to a PC. And with a Bluetooth transmission, thus the whole device is already decoupled from main voltage sources, so it's safe in terms of voltage supply. So I ran quickly through the different details of the hardware setup. So I said already we have the 5 microphones connected by cables to the main PCB. We have the signal conditioning, which consists of an amplification stage between 40 and 60 decibel, and filtering here on the in the main part, in the analog part, between 20 and 2000 hertz. The analog to digital conversion is done by using the MSP430 by Texas Instruments. And as I said, we have the Bluetooth connection with BT 2.1 and enhanced data rate, so we can actually stream the raw data from the device to the PC. Yeah, the energy supply is with 2 batteries in series, and the whole device is fixed by a chest belt on the chest. So the mainboard and the microphones are, for that we use adhesive tape. Finally, we do the data analysis by MATLAB offline. So we will, as I will show in the next slide, record 2 different data signals. So first of all, from our prototype and from a commercial reference system. We use a cuffing signal at the beginning of the measurement, so we can afterwards by hand synchronize the 2 signals. And as we focus in this particular application on the hard sounds, we do an additional filtering here from 10 to 70 hertz, which are the main frequency bands for hard sounds. For evaluation, we use this setup. So I said we compare our signal to the measurements of an electronic stethoscope that is used in clinical routing by Littman. We try different isolation or test different isolation layers. So first of all, of course, direct contact, so which should provide the best measurement results. Then plastic foil, which would later be used for fixing the microphone on the body surface. And finally, plastic foil and T-shirt. So if we want to measure the hard sounds through codes. We further have tried several measurement positions, all located here on the chest. So center of the sternum at air point, which is often used for heart sound analysis, and at the apex of the heart. And we have also looked at the same or the corresponding positions on the back. So first of all, concerning the results, we have a look on the comparison between our measurements and those of the reference system, the electronic stethoscope. And you see in the long test measurement, there's quite a good agreement between that. Sometimes even higher amplitudes from our signal. If you have a look on a more detailed view, then you see also good agreement. So you also see the different oscillations of the different hard sounds. So we have hard sound number 1 and 2, and here comes the next heart cycle that is measured by both of the systems. So in terms of quality and of the morphology of the detected heart sounds, we can say that our system is in good agreement to the commercial reference. Then we have, as I said, checked different positions. So first of all, here for Erb's point on the chest and on the back, and yeah, you see that the heart sounds are highly or far more pronounced here in the ventral position than in the dorsal one. Of course, because the heart sounds have to travel through the lung if we want to record them at the back. So if you don't need a dorsal position, for example, if you want to treat Alzheimer patients, and it would be more appropriate to put them between the shoulders so they don't remove the plaster. So if you don't need to do that, it's highly recommended to use ventral positions. So we come to the matrix with the comparison of different isolation layers and of the different ventral positions. So first of all, not very surprising, if you increase the layer, thickness of the insulation layer, then of course the signal amplitude decreases, so from left to right in the tendency, and sometimes also the noise level increases. But, and that's the good message here, you can indeed use all of the different insulation techniques and still get a sufficiently pronounced signal. And what is also interesting is, and this aims for more for the part of directional filtering, is that the ratio of the amplitudes of the different heart sounds changes if you change the measurement location. So here for the center sternum, particularly here in this part, so the S1 and S2 heartbeat or heart sound are quite similar concerning the amplitude. And if you move to the cardiac apex, the heart sound number 1, S1, becomes much larger than the second one. So this is what I actually just said. So we have a good quality for all isolation layers. So we can use our prototype both in direct contact, fixed with the adhesive tape, and measuring through clothes. And we have the effects of the different measurement positions that result from, on the one hand, the different sources of the heart. So S1 comes from the atrioventricular valves, S2 from the semilunar valves, and the different measurement positions. So first indication that we might indeed do positional filtering by comparing the amplitudes. So coming to the outlook, so I have proposed a small size wearable system for the capture of different types of thoracic sounds. When compared to the reference stethoscope, we find the signal quality comparable to between the two compared systems. We found that, of course, the ventral position is recommended compared to dorsal positions in case that you want to analyze heart sounds. And we have found a good signal on sufficient signal quality for all three fixation techniques. Now we come to the next steps. Of course, we will first aim to get more noise cancellation by using the fifth microphone that aims away from the body and wants to reduce the noise from the environment. Then, of course, the directional filtering by fusing the different microphones and trying to focus on one single sound source. And as I said in the introduction, we would like to fuse the data with signals from other sources like ECG and activity, and finally integrate the whole system into the data communication platform that provides the information to the treating personnel. So thanks for your attention, and yeah, hope for questions.